Hi everyone. I'm supposed to give you a lecture now. The topic I decided on is on-disk data structures. On-disk data structure, unlike an in-memory data structure, is one that's optimized to be used on disk, which or some sort of storage device that has some different properties from memory. Now, why would we want that? Well, here I just ran a quick benchmark on some devices I had lying around at home. And on a spinning Rust disk, I got something like 65 operations per second, where an operation is reading a 4K block from disk into memory. On an SSD, the one I had at home had performance of around 11,000. And yes?
Excuse me, can you explain a bit in detail what these numbers are? Because
yeah, so I'm explaining. So the pure depth 1 numbers are when your program sends a request, waits for a response from the disk to get back, and only after it has finished sends another request and so on. This one is supposed to be a queue depth 2, not 1, which is when you have up to 2 requests that are in flight. So you send the request, when one of them returns, you send another one, and so on. Here we have a queue depth 4 and a queue depth 32. And as you can see, with spinning Rust disks, they don't really get that much faster. Oh, this number is also supposed to be 104,000. Yeah, so SSDs get faster, get quite a bit faster, up to a queue depth of around 8 or so. Up to that point, they scale almost linearly. And RAM also scales linearly quite a bit as well, until you reach your memory throughput. Now, why, given these numbers, why the hell would we ever want to use any of these two? Because they are slower in every possible way. In fact, even RAM isn't the fastest thing. The L3 cache of your CPU is even faster. So there's no reason to use RAM either. This is faster, you should just use that. Well, there's one obvious reason, and that is cost. So spinning Rust disks are still quite a bit cheaper than flash, which is cheaper than RAM, and L3 cache is obviously very limited and very expensive. So this presentation will be about data structures that are optimized more for these two and less for these two. The first thing we will look at is something that's actually not the simplest data structure, a sorted array. So we will look at how to sort. Alright. There are some conventional sorting algorithms that I'm sure all of you are familiar with. Those are heap sort, quick sort, and merge sort. And when we apply them on disks, we get some interesting, well, they have different complexities. If we have an I/O block size of B elements, with quick sort, with heap sort, we have lots of random accesses. Effectively, each comparison is a random access to the heaps, and you're jumping everywhere. So you get O of n log n accesses. With quick sort, things are quite a bit better because partitioning is done sequentially, so you can read a block of numbers. Like you have your array that consists of many elements, and you read a whole block at once, and partition it into 2 other arrays. And so on for the next one. So we get an O of B speed up because of the sequential accesses. Things are similar with merge sort, where Again, merging is merging only does sequential memory accesses, so we also get that factor OB speed up. Now let's see if we can do something better. All of these use log base 2 because you split the array in 2 parts. So if you're doing merge sort on a billion elements, no matter what you do, you have to read and write every element back from to disk and back 30 times. And we'll try to improve on that. The idea is that we will actually use them around the main memory we have in order to slightly improve the number of times we read and write back. The algorithm is multi-way merge sort, but the way it works is quite simple. Just what? Well, we start by reading as much data as we can fit in memory, and we sort it in memory. It doesn't really matter what algorithm we use. And what this effectively means is that we skip the first few iterations of having to read and write to disk. So if we have a terabyte of numbers, so some number of hundreds of billions, and a gigabyte of memory, we will only end up with 1,000 arrays we have to sort. So even if we do a regular merge sort afterwards, we'll have 10 iterations instead of 30-something. But then there's another interesting bit, which is that we, instead of only merging 2 arrays at a time, we merge many. So So we have our sorted arrays. We have lots of them. And what we do is we start by reading one block from each array. So we just read the first block from each one. And when we have, after that, we just read individual elements and write them to the output array, again, block by block. So and whenever we reach the end of one of the blocks we've read, we just read another one and another one, and so on. So because of this, we have the log is base m because we merge m arrays at a time. In memory, we could use something like a heap or a tournament tree to do the arrays. Yeah.
Isn't the time complexity n block n times m, because on each step you get to compare n blocks?
I'm only counting the disk I/O complexity, that is the number of times you read and write blocks on disk, because as I showed here, disk is still many orders of magnitude slower than memory and the CPU. So effectively you have, in terms of time complexity, as element comparisons, you have another log m factor here, but that's only for the things you do in memory. The number of disk reads and writes you do is n log m n divided by b, because you always deal with b elements at a time, and each element goes through log m of n merges. Now, I hope now you all understand this algorithm.
Mhm.
Any other questions? Okay. So the goal of this was to try to figure out what we were dealing with and how we have to optimize our algorithms. Now we will look at some dynamic data structures. Say you just want to store some keys and values and have fast lookup on keys and ranges of keys. So you'd use some sort of sorted data structure, like maybe a self-balancing binary search tree. Yes, that can be used, but in a typical binary search tree, the node size is something like 32 or 64 bytes. And when you send a request to the disk, it only deals with multiples of 4096 bytes, so there's lots of waste, lots of data you're reading from this that isn't really useful. And the goal here is to have a data structure that, again, reduces this factor here, reduces the depth of the tree by having larger nodes. One such data structure is the B tree. The idea is that instead of just storing one key per node and have two children, we store more keys and values. So a node has up to m children and up to m-1 keys. And n can be quite large. For example, for a 4K block with say 64-bit keys and values, so 16-byte total key value per size. A reasonable value for m might be something like 100. And we'll see that the depth is quite a bit lower for. So, for example, if you have a billion, or if you have a trillion elements, log base 2 would be 40, but log base 100 would be 6. And these trees also have a nice property that they are always uniform depth. We'll see how and why that's the case, but every path from the root will have the same length, so they are automatically always balanced. This is what the B tree looks like. I hope I don't have any errors in there, but we have the root. Some nodes have fewer than the maximum number of elements. I think in this case the maximum is 3 keys per node and 4 children. And in this case this also includes the leaves, but in a real implementation. Yeah?
In each and every node we can have up to, let's say, 3, 4...
In this case it's up to 3 keys and up to 4 children.
But let's say, could we have 2 elements in the root?
Yeah, we could. Yeah.
Okay.
The root is just a regular disk block, so you should store as much as you can. In fact, here I said that you try to keep between m-1 divided by 2 and m-1 elements per node. In the case of the root, it might have to be smaller. So here I will show how we do a B-tree insertion. The way we do it is we first find where to insert a new element into a leaf, and then try to fix the tree invariant that nodes aren't too big. And in some cases, the height of the tree will increase. So here we are inserting 18. But we have a problem because this node now has 4 elements, and that's not supposed to happen. We're only supposed to have up to 3 elements. So we'll have to split it into parts. One will be 17 and one will be 19 and 20, with 18 as a value between them. And that 18 will be inserted right here, like this. And again, we have the problem where we have more than 3 elements in a single node. And again, we split, say, this and this with 16 between them. And yeah, here we have it we have 23 keys on a tree that only has a depth of a height of 3. so quite a bit better than the 5 we would need for a binary search tree, for a perfectly balanced binary search tree, maybe up to 8 for a non-perfectly balanced one. And if the root becomes too big, so if the root had 4 elements, then we'd split the root, and we would create a new root node with the separator in it as the only key, and 2 parts of the old root as its children, so we would increase the height. And as I said, the invariant is that all nodes have up to n-1 keys, and everything except the root has at least m-1 divided by 2, which gives us this depth bound. And because of the way we do the splits, you have each node retains its subtree height for its entire existence. So a leaf will always stay a leaf. This node will always have children that are leaves, and if it splits, it will split into multiple nodes whose children are all leaves, and so on with this one. It will always have a subtree height of 3. That's the uniform depth. Any questions? Yeah.
So the height always stays the same.
The height for a single node, it will keep its the height of its subtree. So if this node splits, it will split into 2 nodes whose leaves are children, whose children are leaves.
Oh.
And we never change the heights of subtrees. Yeah.
How this looks like in the code?
Quite messy.
Using the pointers.
So the way I implemented it when I tried this is I had a node with a fixed size array. I had this node structure with a fixed size array of keys, which are stored in line, so just an array of ints or something, and an array of pointers for the children. So yeah, pointers. And to save memory, you can use a different struct for the leaves, because leaves don't need to have any pointers. There isn't anything below them. Yeah.
What when we pull up a first node?
Sorry, when we what?
When we pull.
When we fill the root. Or
yes, the root.
Yeah. So when the root fills up, you split it into 2 nodes, and the separator that you remove, like how here we moved the 18 up 1 level. So the separator becomes a new root node with 2 children.
And whole tree is 1 depth.
So yeah, so and when you do that, that's the only case where you increase the entire tree. But only the new node has increased height, and the old parts of the root are still at the same level above the tree, above the leaves. Any other questions? Yes.
Let's say we have to put an element above. How do we find its place?
Well, when we have to put an element, what do you mean put an element?
Let's say you have to split and you have to put the middle element up in the parent.
Well, just insert it. So here we had this node split. Here's the link. The link goes here, so we insert it here.
Oh, okay.
All the keys inside the node are sorted, and they act as delimiters of the node below them. And you can experiment with different sizes for the nodes. I actually implemented this some time ago, and even when you're working with a tree that's in memory, you can use quite big nodes, something like 50, up to 50 keys per node, and it's actually faster than binary search trees. I think it was something like 2 or 3 times faster than ABL trees. both for insertion and for lookups. However, deletion, however, is
But if you're looking for a specific element,
Yeah.
When you reach the desired node, wouldn't you have to go through all the keys to find it?
Well,
Wouldn't that
so
increase the
let's say
complexity?
we're looking for 11. It's not to the left of 10 because it's larger than 10, and it's not to the right of 16, so it has to be between them. We descend here. Now we check 13, descend left. Here it is. So these are separators. Everything that's inside this sub-tree is between 10 and 16 in terms of values. Everything that's to the right of here is greater than 16. Everything that's to the left of 10 is less than 10. Everything that's on this side is less than 13 and greater than 10. So it's a bit like a binary search tree, except that it's a generalization where you have more keys per node. The lookup. You do have to scan the entire node, but that's quite fast because the node is what, a 4K, and scanning 4K of memory is really fast. As I said, even in memory, where you're not dealing with disk I/O, a simple loop is faster than binary search for up to 100 elements. Yeah, so deletion is quite a bit more complicated. First, if we're deleting from an interior node, well, we can't do that because we're trying to delete a separator. So we'll need to find a leaf to replace it with, just like we do with binary search trees. And then we might need to do some rebalancing, which is also quite complicated. And in some cases, we might have to decrease the height if the root node becomes empty, as it only has a single child and no keys inside. Because of this, many implementations just don't delete B-tree, elements from B-trees. Some only delete from leaves, and, well, in the case of B plus trees, PostgreSQL only deletes nodes when they become fully empty. It doesn't try to maintain the invariant for the minimum size of the node. And what you need to do is just rebuild the tree every now and then. Or maybe you can just keep the leaves intact and rebuild everything above them, which is quite fast because only 1% of the nodes are interior nodes and 99% are leaves. Anyway, if you do want to implement deletion, let's say we're trying to delete this 18 here, we have to find a victim. So we pick this number here, we move it up to, so we just pick the first element, the rightmost leaf key of the left subtree, or we could have picked 19, which is the leftmost element of the right subtree. Either of them works. So we replace 18, 17, and actually delete 17. Now we have a problem because we have an empty node, or, well, a node that's smaller than the minimum size, which is in our case 1. And we have to figure out a way to fix this. There are two possibilities: rotations and merging. A rotation means that we pick a sibling, in this case this one, and the separator, and we try to somehow figure out what to do. That is, we move something into the separator and move the separator down. So we end up with this. In some other cases, we might instead merge two siblings if they're and turn the and in that case we also need to move the separator inside the newly created node. Any questions? as I said, if you're implementing B-trees, you probably want to not have to do this. It's complicated. An interesting property B-trees have is that in the case of n equals 4, that is up to 4 children or 3 keys per node, they are isomorphic to red-black trees. Do you know what isomorphism means?
No.
Well, there exists a one-to-one mapping between the two that preserves structure. So here's our B tree as a red-black tree. This is a black node, and its right child is red. Its right child has 2 black children. This black node, well, one of them is this one, which has a red right child. This one doesn't have any red children. Instead it has 2 black children only. Basically, the middle, if you have a node that has 3 keys, the middle one is black and the other 2 are red. Or if you only have 2, then one of them is black and the other one is red. It doesn't really matter which one. The result is that we keep the red-black tree invariant, and the red-black tree invariant is that for every path from the root to a leaf, there must be the same number of black keys. Well, there's only one black node, black binary, red-black tree node per B3 node, and B3s have uniform depth, so we have this property. It also turns out that the B3 insertion algorithm is the same as the red-black tree insertion algorithm, as in the changes they perform to the map over the isomorphism. So if you convert your B3 to a red-black tree to insertion and convert it back, you end up with the same B3 you would have if you just did the insertion from the B3 and vice versa. I think for deletion it isn't exactly the same. The red-black tree deletion algorithm is also complicated, but a bit simpler, and does some changes to the tree that can't be performed as nicely.
Is this property actually used? I mean, n seems rather small.
Yes, so nobody really uses B3s of this size.
Yeah.
Well, unless maybe you're trying to fit a node inside a CPU cache line. So if your CPU has a cache line of 64 bytes, that is, when you read from memory, you always read 64 bytes, no matter how many of them you actually use. It might be a good idea to use a small B3. But yeah, it really depends on what you're doing. I think even with memory, and even when working with in-memory data, a slightly larger n is often a better idea.
Yeah.
I think the map type in Rust programming language uses a B-tree instead of a binary search tree, but I'm not sure what the exact node sizes they were, but they were quite small. Well, now we'll talk about a slight variation. Oh, so actually, any questions? Yeah.
So if m was equal to 2, would that B3 would be the same as a normal binary search tree?
No. Well, no, because when m has to be at least 3. Because here, if you have m equals 1, you have a minimum number of 0 keys per node, and that means that you can theoretically end up with an infinite chain of single child nodes with 0 keys in them, which is not good. So with n equals 2, this is a perfectly valid B3, and it's not something you want.
For m equals 3 is
For
binary
m,
tree.
yeah, for m equals 3, you end up with a different tree where you can have. Oh, sorry, this one is n equals 3, so it has to be this one. Sorry. For n equals 3, you have a different data structure that's a special case called, I think, 2-3-3, where each node contains 1 or 2 keys and has 2 or 3 children. It's, yeah, probably a bit easier to implement efficiently, as in you don't have loops. Yeah.
The normal binary, self-balancing binary search tree, every single node who did it have 2 or 0 children, right?
You have a node with 1 child. Let's insert 1 into an empty binary search tree. We don't have much choice. We create a root with a value of 1. Now let's insert 2. Done. Well, you could perform a useless rotation, but it's not really that. It's not a good idea. So you end up with a node that has 1 key and 1 child. So here you have an empty node, and big trees don't let you do that. You don't have uniform depth because this path only has goes out of the tree, but only has 1 node on it, whereas the other ones have 2 nodes. Or you could have this, again, balanced binary search tree, as balanced as it can be. That also has different depths on different sides. So it's only the only thing I've seen that shows some similarity between B trees and binary search trees is this isomorphism where up to 3 red-black tree nodes form a single B tree node. Basically a black node and its red children. Now B plus trees are quite similar to B trees, but they have one important difference, which is that you don't try to store values in the leaves. Sorry, you don't try to store values in interior nodes. Instead, all of the values and all of the keys are stored in leaves, and you have duplicate keys inside the interior nodes. For example, you'd have something like these leaves, and so effectively each key that's stored inside an interior node tells us what the smallest key of the entire subtree is, so in this case 5. And when inserting, again, we try to find the leaf where we want to insert. Say we want to insert 4.5. Well, 5, so we have to go left. We insert it here, but the node becomes too big in the case of the limited 4 keys per node, so we split it into 2 nodes. like this. A much simpler split because we don't have to move anything. And we also need to insert new delimiter here. To new node. So only the leaves are different from a normal B3. Everything up is basic. Oh, here we also need to do a split, sorry. Yeah, here we will do the split the same way as a regular B3. So new root.
Will still be 8 in this case.
No, because this 8 indicates that its right child is starts with 8, and this 5. So the leftmost leaf of the right child of the child that's to the right of 5 is 5. The leftmost leaf of this subtree is 8, and so, and the leftmost leaf, the right child of 3 is 3.
Why the number 3 appears times?
Because it's so in a B plus tree, all of the keys and values are stored in leaves, and some keys are duplicated up in the interior nodes.
So B plus trees are like segment trees.
Yeah, I guess they are a bit like them. So yeah, depending on how you implement it, you might include the first key of the left child as well, but it's optional, and you never actually need to use it. So the original implementation, the original tree describes and suggests that you don't store them. And deleting from B plus trees always starts by deleting the thing you want to delete from the leaf. And some people just leave it at that. You might do something like a B3 deletion in case. So you might want to merge adjacent leaves if they become too small. So if we delete 7 and 8, we might merge and 9, I guess. We have to delete a lot for merging to be well, so we merge these two nodes. And then we have to figure out how to fix, well, for the delimiters, you can just remove them. If you store them explicitly, it's actually a bit easier, I think. So yeah, slightly one advantage B plus trees have is that if you have small keys and large values, by only storing values in the leaves and not storing any values in the interior nodes, you can have a larger value of m for the interior nodes, so the height should be a bit lower. Say if your key size is 8 bytes and your value size is 64 bytes, with 4K blocks in a B3, you delete it to something like, I don't know, 50-ish children, whereas with a B plus tree, you can go to 250.
In all these cases, this complexity is how many times you have to reblock
Yes.
to find something.
Yeah. So here we have relatively large blocks we read from disk, and we want to minimize the number of times we do that, and we assume that processing a block takes constant time. Any questions? Anyone not understanding anything at all? Okay. This isn't something that makes sense for someone to write in 5 hours. I mean, it's these data structures are used for projects that take months or hours, so, or years. Databases tend to use them. File systems also use them. And yeah.
So they illustrate how normal data structures would look like if theoretically we could perform M operations in constant time.
Well, yeah, I guess. Yes.
So this is used if you could, let's say, compare m numbers in a constant time.
Yes, but in this case you kind of can, because the majority of the time is reading from disk, and when you read from disk you have to read large blocks of data. You can't. Well, reading 1 byte takes exactly as long as reading 4K. And let's say if you're dealing with spinning rust disks, so hard disks, reading a megabyte is only ever so slightly slower than reading 4K.
You use this only when you cannot get whole data in
it sometimes makes sense for you to use a small m, because with memory the block size is 64 bytes. Reading 1 byte from RAM, it takes about as long as reading 64 bytes. So it really depends on your use case and how your code is written and how exactly you're comparing the keys and so on. You might be able to optimize your program by using a data structure with slightly larger nodes. As I said, I just wrote a naive implementation of B trees and a naive implementation of AVL trees. And with an AVL tree node size of 40 bytes and a single key value pair in it, and a B tree node size of 1024 bytes, and tens of key value pairs in each node. The B tree, even when working in memory, was 3 times faster. But it also depends on what computer you're using. When I tried it on another one, it was maybe only 80% faster. So yeah, with modern CPU architectures, you can do something like load 8 integers from a contiguous block of memory and compare them against something. That's SIMD extensions that these CPUs have. Next thing which I wanted to look at is data structures that are optimized for writing. So the primary operation will be dealing with is upsert, in which we have a key and we want to do something with whatever is stored in it, which could be to insert it or to overwrite it or to modify it or delete it somehow. But when doing this upsert operation, we don't really care what the original value was. We just want to record somewhere that we've done, that we need to do this update. And the most basic variant of a log-structured merge tree is a sequence of arrays, where the ith array has 2 to the power of I elements. And smaller arrays contain newer updates than larger arrays. If we do have read operations, we might need to construct a bit plus tree-like index on the arrays, but the arrays are never dynamically updated. We only do merge operations. So this is an example LSM3 that's full because that has all the arrays populated. So yeah, I just inserted the numbers from 1 to 15 random order. Let's try to insert 16. Well, this array is now too big, so we merge it with this one. This array is also too big, so we merge it. And this array is too big, so we merge it with the next one, and we're done. This is the worst case of inserting when you need to propagate it in the entire tree, but half of the time you'll just add it to the first array and you're done. So, in a realistic implementation, you wouldn't actually have all these very small arrays. Instead, you'd have a large in-memory array to which you append stuff, and when it gets full, you only then write it to disk, which gives you the speed up of not having to do a single I/O for each and every element. Because in a bit tree, inserting a single value takes depth IOs. In an LSM tree, inserting a single value takes log n divided by b IOs on average, because if you store them block by block, because you store a whole block of values at once. Well, unlike this example. Some other things you could do to speed LSM trees up is to have more than one array of the same size. So, and when you have too many arrays of a given size, then you merge all of them together using the multiple-way merge algorithm we talked about. Alternatively, you could have them grow faster than a factor of 2. But querying LSM trees is more complicated, because instead of having to do a single log n-ish lookup in a single array, you have to do multiple lookups. And so in order to support lookups, you'd have to build a b+3 like index on each array. So you have index node that contains every bit element, then another layer of index nodes that contain the first keys of each belongs to all of them, and so on. Any questions?
What is this used for?
So
you want to use this
for when you're processing lots of data and you want to somehow aggregate it or merge it or whatever. So when almost all of your operations are absurd, like so insert, modify, or delete without reading the value, and you have very few reads compared to the number of writes. You do have a terrible trade-off, because that, in the sense that reads, lookups are really, really slow. Well, that's why there's another data structure, the epsilon trees. Is it because it's yet another B something tree? Or? I think there are also a few other kinds, but I think there were also B star trees, and there was another kind that was in a research paper published by Microsoft a few years ago, but I haven't actually read about them yet. So lots of B something like trees exist for different use cases. The idea here is that instead of just storing keys and values in the nodes, and instead of storing many keys and values in the node, we store slightly fewer. So instead of storing, instead of having m be on the order of b, it's on the order of b to the power of something, some epsilon that's less than 1. 0.5 is a good idea. So the m you would use is about square root of the value of m you use in a regular P3, which means that the depth is, the height of the tree is 2 times larger. But So yeah, reads become 2 times slower, but we'll see that writes become quite a bit faster. In this case, square root of b times faster. The core idea is that in each node has its keys and children, but it also has a larger buffer for storing updates. So key value assert and so and if you have something like square root of the block size in terms of keys, then the block size minus square root of the block size is this space here used for pending writes that eventually need to be propagated to the children, but we don't do that yet. So you do lots of writes at the same time by just putting them in the root node and dealing with them eventually. But eventually the root node will overflow. You won't be able to put any more writes in it. So what you do is you pick the child it has that has the largest number of writes pending for it. So let's say it's this one. You pick all of the writes that have to go to this child, remove them from the root node, and propagate them all at the same time with a single I/O. And because you have, oops, what did I do?
Reminder next week. It's ready, start ready.
No, it's up. Oh. Okay. So
Yeah.
we have some, yeah. So we have something like b minus b to the power of epsilon writes inside the buffer, and we take the child that has, and there are b to the power of epsilon children, so at least one child has to have this many well, at least one child has to have b to the power of 1 minus epsilon. Well, minus 1 if it doesn't, if it divides exactly. Writes going to it. So with a single I/O, we remove them from this node, and with a single I/O, we add them to the child where we need to add them. And again, that child might overflow, and if it does, we propagate propagate some of its writes to one of its children that has number, and so on. And this really works better if you have very large nodes, say 64K or a megabyte or something like that. And yeah, any questions?
Who invented this?
I don't remember, sorry. I can find paper.
People we can
Yeah. So apparently it's these guys. Yeah. A data structure invented by, as some of you noted, data structure invented by that many people is probably not completely obvious. And I guess here we can see from the reference. So this is the original paper that describes the epsilon trees, and they have some references from 2015. So this is also quite a new data structure. I heard about it in university. Yeah, so they show the complexities of operations. So if you have a p epsilon tree, this is how the complexity looks like of inserts, range queries, point queries, and so on. In particular, in the case of epsilon equals half, and with the B tree, the asymptotic complexity is the same because it's only a factor of 2 difference in depth. But inserts are square root of b times factor because you do multiple inserts with the same IO. And here they are showing the complexity of LS entries, which are a bit worse. And the other thing is that they're showing is LSM plus BX. Can any one of you guess what this BX stands for? Huh? No, it's not that. It stands for Bloom filters. So the last topic I'll tell you about is probabilistic data structures. In particular, we will look at probabilistic sets in which we can insert stuff, and we can check if stuff exists, except they might sometimes lie to us. We can only accept false positives, that is, the set can tell us that something is there when it isn't, but we're not willing to accept any false negatives. So if we have inserted something, then the set must tell us that it's present. And we'll see that these sets are way more compact than just storing all of the elements. In fact, in the case of Bloom filters, you only need to store 10 bits per element, no matter how big the element is, in order to get a false positive rate of around 1%. The way a Bloom filter works is, well, we have some array of bits that's not, well, I think it's not possible to resize it. You have to pick it in advance based on your expected number of elements. And we have a bunch of hash functions. The number of hash functions determines the optimal number of hash functions can be picked based on what error rate you want to have. So it's also I think the optimal number of hash functions is equal to the number of bits per element if you size your filters correctly. So in this case, for a 1% error rate, we have 10 bits per element, so 10 times n bits and 10 different hash functions. Each hash function gives us a number between 0 and n. So in order to insert some value, we just compute all hash functions on it and set the corresponding bits to 1. The hash function tells which ones. How do we test if an element is present? Well, we check if all of the bits that must be set are set yes,
B is the number of hash functions, or what?
K is the number of
Okay.
hash functions.
Well, what is B exactly?
Wait, what?
B.
B. Oh, number of bits per element. So for B bits per element, default positive probability is something on 1 divided by 2 to the power B divided by, I think it was log base 2 of E or something like that. And the problem with Bloom filters is that once you insert something, you can't delete it. So you can't just go and set the bit back to 0. This is because of collisions, and what collisions do Bloom filters? Let's say we have our filter of eight bits, and we have our hash function. Well, I really don't want to compute hash function on the whiteboard, so I'll just imagine the values. And let's say that k is 2, so we have 2 hashes for each x. And we insert x1, which hashes to, say, 0 and 5. So we set bits 0 and 5 to 1. Now we insert x2, which hashes to 2 and 3. So we set 2 and 3. Now we check if x3 is present, and x3 hashes to 0 and 2. So we check. Bit 0 is set, bit 2 is set. Therefore, the filter says that x3 is present. Well, it actually isn't. That's how you get errors when you mix different hashes from different inserted values.
But when we have more hashing functions, the error is...
The error rate goes down with the number of hash functions, but you also need to have a large enough array, because eventually, if you just insert 100 values, no matter how many or how few hash functions you have, the array will just fill up and the filter will say that everything is present. So yeah, for a Bloom filter, m needs to be b times at least the number of bits, the number of at least k times the number of elements. So yeah, and this also determines the cause of the probability. If you go over the optimal number, if you go over the predetermined number of elements you expect to have, the error probability goes really fast. Goes up really fast. So ideally, if you have a fixed data set, that if you already have your data, then after you know its size, you can compute what Bloom filter size you want. In the case of LSM trees, after you've merged the array and discarded any duplicates if you do so, then you can construct a Bloom filter for each of the levels. And by keeping the much smaller Bloom filters in memory, you can quickly decide which of the LSM tree levels to look up and which ones not. So you can make it so that on average you will look up, say, 1.5 levels per element. And as I said, deletion is not possible, because if we insert x4, which hashes to 0 and 4, so we set 0 and we set 4, now we can't delete x1 anymore, or x4. Well, we can't know that it's safe to just clear these bits in order to delete x1, because some of them might have been set by other values we've inserted. Yeah?
what if instead of 1 bit we were to keep in all of these the amount of times we inserted something there?
Yes, that works, but then you have the memory usage increase log n times because you need counters that go up to the number of elements you have instead of just individual bits. There's another. So in terms of well, I think there is a proof that for any probabilistic data structure of this kind, the best you can do is an error probability of 1 divided by 2 to the power of b. So a Bloom filter uses 1.44 times more bits than the theoretical best algorithm that could possibly ever exist. Which is not that bad. I mean, it's only a constant factor worse. For many things, we don't even know if the asymptotic complexity is exponential or polynomial, so yeah. Another algorithm the last thing we'll look at today is cuckoo filters. Which, do you know what cuckoo hash tables are? For each, in cuckoo hashing, what we do is we have 2 hash functions, and we have our table, and for a single value, the 2 hashes tell what are the 2 places where it's allowed to go. And so individual slots of you just have a fixed array that's your hash table, and for each element you compute the 2 hashes and insert it into either of the 2 slots. Now, when doing a lookup, you only have 2 places where you need to check. So your lookups are constant time, and they're guaranteed constant time. There are no degenerate cases where you might end up traversing the entire table, which is good. However, inserting may require shuffling existing elements. Say, I wonder if I can give a nice example. Yeah. Say we've inserted this guy here, and this guy here. Now we can't insert this guy because both of these slots are taken. So what we need to do is pick one somehow and kick it out and move it somewhere else. So we insert this guy here, and then we need to reinsert this guy somewhere else. And sometimes we can do that. It turns out that if you have, well, I'm actually lying here, this isn't true at all. If you really do have one slot, so if you really do have 2 slots for each element, then you're very likely to be able to build the table if you have a good hash function and the fill rate is up to 50%. But if the fill rate goes above 50%, you have a negligible chance of being able to construct the table. It's basically like the probability of having a perfect matching in a random bipartite graph. So what we can do instead is have a slightly larger table that can accommodate up to 3 or 4, or yeah, that's usually what people do, up to 3 or 4 elements per slot. If we do that, I think then we have very good probability of being able to fill the table up to 90-ish%. So 90% of all the 3 times the number of rows slots would be taken, which is quite a bit better than 50%. So With a cuckoo filter, we do something quite similar. For each element, we have a single hash function, well, a primary hash function, and a fingerprint function, where if we have if we decide that we want to have 8 bits per element, then fingerprint must be 8 bits. So the length of the fingerprint determines how many bits per element we store. And we have a hash function that hashes fingerprints. And if the fingerprints are small, this could be a random pre-generated random table or whatever you want. So a good random hash function and a good random fingerprint function are the important things you need. And the way we insert an entry into the filter is we store its fingerprint at either of its allowed positions, where the second hash is defined this way. What this lets us do is, well, here we only see the fingerprint of the value. We don't see what the value is. But we also know that this is the first hash of x. And by knowing the fingerprint and computing the HF of the fingerprint means that we can figure out what the second hash is. So if we decide to kick this value out, we can immediately find where its other place is, where it can be moved, without storing the full value. And yeah, obviously without any pointers or anything, we just store fingerprints. Deletion is easy. We just find where we store the fingerprint, which is in either of these, and remove it. Done. And now the false probability rate. For a b-bit fingerprint, it's 1 divided by 2 to the power of b minus 1, which is quite a bit better than b divided by 1.44. So, assuming a fill rate of 100%, which we don't have, then we'd have a false positive probability that's only 2 times higher than the theoretically optimal probability. However, it's actually something like 1 divided by 2 to the power of b divided by 1.1 because of the fill rate minus 1. So slightly, well, not quite as bad as a full filter, but still not quite perfect. However, we could increase the number of slots. I think for something like 4 slots we get, I think it was maybe 95% success. Well, 95% fill rate, and so on. Or we could add more hash functions. So we have 3 hash functions instead of 2. So that would probably require some more complicated math around fingerprints. The point is we can get arbitrarily close to this number here being 1 by just increasing the constant factor of how many things we need to check. And yeah, if we do fail to build the table, we just change the hash function and try again. As I said, with a decent-ish hash function, the probability of succeeding if you're under the critical fill rate is very close to 1. And yeah, I guess this won't work if you have duplicates, so you do need to detect the duplicates manually before inserting them. Any questions? Any comments? Was I going too fast or way too fast?
Sorry.
Yeah.
What is complexity of caching?
I assume it's I assume that the complexity of computing the hash function is constant. So, yeah, in this case, I haven't talked much about computational complexity. We have a constant number of disk IOs, or a constant number of places where we would read from storage if we decided to put this into some sort of slow storage. Or even if you put this in memory, you only need to fetch 2 cache lines, which is decent. Unlike Bloom filters, where you need to fetch k cache lines. There are variants of Bloom filters that store the bits differently, so that you need to load from pure memory locations, but they are slightly less efficient. Yeah, this is everything I had prepared.